Good morning, everyone. Today we will continue to talk about wave optics. And like in last class, we have already talked about what is light and some like wave model for the light. And today we will continue to talk about that. Okay, let's share my screen. Okay. Firstly, let's check today's goal. Yeah, before we check today's goal, let's review like what's the goal for the chapter 17. Yeah, like the chapter 17 we mainly talk about wave optics and we mainly focus on understanding and applying the wave model of light. Yeah, actually if you familiar with like light and you will know like the light actually he has different model. He has different models because like a light is a kind of a wave. Also, it is kind of like a particle which can travel in a straight line. So mm, or maybe the light and the light can have the both features and characters in this chapter we mainly focus on the wave model of light. Yeah, like light is just similar water and sound. Water wave, sound wave. Yeah, they have some they have the wave model like for the light. Okay, let's continue. And yeah, today's goal, sorry, I think this one is uh, okay. This is 10. It's not nine. Okay, yeah. So this is 10. Firstly, we will review the topics. What is light? And what is like a double slit interference and diffraction gratings. One more thing, last class I pronounce like this word very weird. And when I realized it, I have already recorded like half the video. So I don't know if you noticed that, but this is slit. Yeah, if I pronounce it very weird, you just ignore that. No, I just talk about the slit. Okay, okay. Again, firstly, we will review what we have already learned in last class, and then we will learn thin film interference, and after that we will learn like a single slit diffraction. Yeah, last class we talk about a double slit, and this class we will talk about a single slit diffraction, and after that we will talk about a circular aperture diffraction. Yeah, the other kind of diffraction. Okay, let's continue. Sorry. Yeah. So, what is light? We talk about this like a last class. Like under some circumstances, light acts like particles traveling in a straight line. And in other circumstances, light shows the same kind of wave-like behavior as sound waves or water waves. So and sometimes the light have both characters and features at the same time. Like they act like particles traveling in straight lines, and at the same time he just some kind of wave-like behavior. Yeah, have some wave-like behavior. So we develop three models of light. Each model successfully explains the behavior of light with a certain range of physical situation. Like the first one is what? Is a wave model. Sorry. It's wave model. Like the wave model, it means under many conditions, light behaviors like sound or water waves. Phenomena such as the bright colors of human bird or the blue sky are best explained using the wave model of light. We introduce some aspects of this model in like chapter 50 and chapter 16. In this chapter, like yeah, we mainly focus on wave opticals. We have our talk about this. And the other model is a RIM model, like a RIM model. Yeah, the behavior of like prisms and mirrors, lenses, and optical instruments like telescopes and microscopes is best understood using the RIM model of light. Actually, this part we will like learn in chapter 18. Yeah, next chapter we will mainly focus on this model. And also, there is the third model. We call it the photon model. Like a modern technology increasingly depends on quantum physics. Yeah, in this realm, light is made of photons, particles that exhibit both wave-like and particle-like behavior. Yeah, photons are the fundamental units of light. Well, much of quantum theory is beyond the scope of this course, but we will like explore some in chapter 25. So yeah, in chapter 25 we will like explore some. Yeah, and so in this class in this chapter we mainly focus on wave model. Yeah. Okay. And so like a NASA class, like we talk about the like what is light. After that, we talk about the double slit interference and diffraction gratings. Yeah, actually, if you like if you review all the video last week, and you will see that the double slit interference, which means uh, here is too small like a distance, and then we will like use this equation to calculate like yeah this if there are two like different slits, yeah, we call it double slits, and then there will be some like there is a phenomenon we call it double slit interference. Yeah, this kind of thing, and we can calculate the y this distance using this equation, and we can calculate the angle using this equation. And for the diffraction gratings, actually it's the similar thing. It's just like you can see for the double slit, it's just a 2. For the like a diffraction grating, it is multiple, like more than 2. Yeah, but it also can like generate some like a phenomenon like these things, and we can actually it is a similar thing. It is a similar like situation, and you can use these equations to calculate like the angle and the like distance between two distance between like two different bright fringe. And the difference between the double slit interference and the diffraction gratings is just like when you increase the like the number of gratings, yeah, like this like a bright fringe will become narrow and brighter. Yeah, does it make sense to you? Yeah, yeah. Did you know why is it just like that? Yeah, because you can see if we use multiple, like here are multiple like distance slits, which means there are multiple like a wave, light wave, and for one like a bright fringe, it will become stronger. But because there are so many like wave here, and there are like also some will be canceled. Yeah, so this one will become like a narrow but brighter. Does it make sense to you? Okay, yeah, this is what we talk about NASA class. Okay, let's continue to talk about something in today's class. Firstly, we talk about the thin film uh, thin film interference. Actually, I don't know if you guys heard about this thing. Like it is kind of like a equal frequency light waves are produced with partial refraction splits a light wave into a reflected wave and a transmitted wave, which means here the equal frequency light waves are produced with partial reflection splits a light wave into two different waves. One is reflected wave, the other is a transmitted wave. Yeah, we will talk more. Like a thin film interference is the interference of light waves reflected from two boundaries of a thin film. Yeah, thin films are used for anti-reflection coatings on camera lenses, microscopes, and other optical equipment. The bright colors of oil, slicks, and soap bubbles are also due to thin film interference. Yeah, those are some like applications for the thin film interference. And let's talk about more detail about thin film interference. Okay, firstly, let's talk about interference of reflected light wave. Yeah, like we said, the thin film with interface will split a light wave into two different waves. One is a reflected wave, and the other is a transmitted wave. Firstly, let's talk about the reflected light waves. Yeah, you can see a light wave is partially reflected from any boundary two transparent media with different indices of refraction. Yeah, you can see like a light wave is partially will reflected from any boundary between two transparent media with different indices of refraction. Yeah, this is some like features for a light wave, because when you hit the surface, there are one is air, the other is mirror. Does it make sense to you? And then there will be some partially reflection wave. The light is partially reflected not only from the front surface of a sheet of glass, but also from the back surface as it exists the glass into air. This leads to two reflection. Yeah, I will show you why it's just like you can see here. There is a mirror. Let me show you. Here, you can see there is a boundary. Sorry. You can see here is a boundary. Yeah, here is a mirror. Here is the air. Am I right? And usually it will some waves when the incident wave meet the boundary, this mirror boundary, and there are some reflected waves will reflected, but there are also some waves they will be transmitted into glass. And in the back of this mirror, there are usually some the other surface. Yeah. Did you know that? Like here is a mirror surface. Actually, there are some coating behind this, and then this wave and will go into this material, and there are some transmitted wave. It doesn't make sense to you. So there is no phase change at a boundary where the index of refraction decreases. Yeah, there are some. This is some features. There is no phase change at a boundary where the index of refraction decreases. Like a light wave undergoes a phase change if it is reflects from a boundary at which the index of refraction increases. Yeah, like a light wave, here is a light wave, undergoes a phase change if it reflects from a boundary at which the index of refractions increases. Yeah, this is some features for this reflected light waves. And the effect of a phase change is to add an extra half wavelength, lambda is a wavelength, divide 2 is half wavelength, which means here you can see this is a reflected rays. Yeah, the reflected of a phase change is to add an extra half wavelength. Yeah, you can see here is the original wave, and here is a reflected wave. Those effect those reflected wave will be added an extra half wavelengths, and this is for the is some features for interference of reflected light waves. Okay, let's continue. For a thin, transparent film, most of the light is transmitted into the film. Some light is reflected off the first boundary. You can see here is a thin film. There is a thin film. There is glass. Yeah. So this is air. Yeah. For a thin film, thin and transparent film. Most of the light is transmitted into the film. Sunlight, yeah, it's just like a reflected, reflected off the first boundary. Here is the first boundary. Yeah, you can see the incident wave is transmitted through the thin film. This is thin film and the glass. This is transmitted, and then part of the incident wave reflects from the first surface. Here, this is from the first surface. Part of the transmitted wave reflect from the second surface. Yeah. Yeah, the two reflected waves will interfere. Yeah, like because here are two different material. One is thin film, the other is glass. So when the like incident wave goes through the film and goes through the glass, and here in this surface it will reflect some, and in this surface it will reflect some. That makes sense to you? Yeah, and those two like reflected waves will interfering. I think that makes sense. Am I right? Yeah. If the waves are in freeze, like they will interference constructively and cause a stronger reflection. Does it make sense to you? Because if they are in freeze, like just like this, yeah, they will like interference constructively and cause a stronger reflection. If they are out of freeze, just like this, yeah, they will interfere destructively and cause a weak refraction or no fraction at all. Like if you can see here, like it's kind of like yeah, this one is constructive. Sometimes if this is no refraction, sometimes it's just like this, like this. Yeah, it is just like a weak refraction. Does it make sense to you? Okay. That is the path length difference of the reflected wave is this one. Yeah, this is the path length difference of the reflected waves, like two different waves. Yeah, here reflect waves. Yeah, I think this image is not very obvious like this one. And this is the one, this is the other. Yeah, you can see here. Here is T. T is the like a thickness of this thin film. Yeah, which means like the path length difference of the reflected waves is 2T. Yeah, because you can see uh, here it will reflected some. Am I right? And then reflected some, and then it will hit this surface and back, which means one is T, the other like the forward and backward is 2T. Does it make sense to you? Okay, because the second wave travels through the film of thickness T twice. Does it make sense to you? Okay, the two reflected waves will interfere. If the waves are in phase, yeah, I think I have already talked about this. Am I right? Yeah. Okay. Yeah. Those two will like interfering. If the waves are in freeze, they will interfere constructively and cause a strong reflection. If they're out of freeze, they will interfere destructively and cause a weak reflection or no reflection at all. Yeah, it's a. I think I have already talked about this just now. Maybe I just like a repeat put this thing here. Okay, let's continue. Like the possible phase change leads to two situations. Like we talk about. If neither or both waves have a phase change due to reflection, the net addition to path length difference is zero. The effective path length difference is just like a 2T. Yeah, like if neither or both waves have a phase change. Yeah, if they have a phase change or no change due to the reflection, and the net addition to the path length difference is zero. So the effective path length difference is this one. Does it make sense to you? If only one wave has a phase change due to the reflection, yeah, the effective path length difference is increased by half length to, yeah, those like path difference will change to this one 2t plus 1 divided 2 lambda. So there are like two possible phase change lead to two situations. Yeah. Okay, the interference is then constructive if like this one equal this one, like this one we have a talk about last week and last week. Yeah, if the interference is constructive, like the difference, like distance will equal like a whole number wavelengths, and if the destructive, it will equal like a whole number wavelengths plus half wavelengths. Yeah, this we have already talked about a lot. Uh, yeah, according to those things, actually we can have this equation. Yeah, these equations. Here, 2t. Yeah, for the like this is for the constructive interference. You can see for the constructive interference, like the difference is 2t, am I right? Here the difference is m lambda. And those things should equal with each other. That makes sense to you? Yeah, but you will see here is n. What is n? Do you know that? Actually, this n we have a talk about in last class. Yeah, this n is the index of refraction. You can see like if this wave enter into glass, yeah, if this is lambda, this is lambda. If it into the glass or other material, and the like lambda will change. Yeah, do you remember that? So the lambda, yeah, it should equal this m lambda, but lambda changed, and the new lambda is lambda divide the index of refraction. That makes sense to you? Okay, yeah, and the similar thing for the destructive interference. You can see this one, yeah, this one equal this one. Yeah, but lambda is changed, so we have this equations. Yeah, those equations help us to like calculate like how like when there will be like a constructive interference, when will it be a destructive interference. Okay, let's let's review some like quick check questions. The first one is the film with thickness T gives constructive interference for light with a wavelength in the film of lambda film. Yeah, here. Lambda film. And how much thicker would the film need to be in order to give destructive interference? Okay, which means here, like we need to find how much thicker would the film need to give destructive interference. So yeah, we need to use this equation. Let's write this down. Yeah. Okay, let's write down the equation here. 2t equal lambda n. Actually, you can see here they give you the film wavelength. So this is just a film like a film wavelength. So which means 2t equal lambda film. Am I right? So t equal what? T equal to lambda film. Yeah, and you can see here m equal what? M equal 0, 1, blah, 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 blah. So which means if it is 0, it will be 1 divided 4. I'm right. It is 1. It will be like 3 divided 4. If it is 2, it will be 3 divided 5. Does it make sense to you? So which one is right? Yeah, only this one is right. Here, and the t should be quarter, like a 3/4, like a 5/4, like that. Does it make sense to you? Okay, let's continue. Yeah, the answer is D. Okay, let's talk about this tactics box, like a 40.1, like how this tactics box just like give us how to analyze thin film interference. Like follow the light wave as it passes through the film. The wave reflection from the second boundary travels an actual distance 2t. Yeah, we have already talked about that. Yeah, actual. Yeah. first step, note the density of refraction of the three media. The medium before the film, the film itself, and the media beyond the film. Yeah, there should be three different media. And the first and the third may be the same. There is a reflective phase change at any boundary where the index of refraction increases. Yeah, we have talked about there where the index increases. Yeah, if neither or both refracted waves undergo a phase change, the phase changes cancel, and the effective path length difference is equal to this one. Like use equation for 70.40. Yeah, this one. Yeah, this one. To for constructive interference, and the other one 40.15 70.15 for destructive interference. If only one, oh, sorry. Yeah, if only one wave undergoes a phase change, the effective path length difference is this one. So use equation 17.40 for destructive interference, and 70.15 for constructive interference, because you can see only one wave undergoes a phase change, which means the effective path length will be this one, and then we should opposite the equations. Okay, do you know why it's like this? If in this situation, use the equation 70.14 for constructive interference, 70.50 for destructive interference, but only one wave undergoing a phase change, and it will opposite. Do you know why? Okay, let's analyze that. You can see here, if it is if the distance is 2t, am I right? So which means 2t equal this one. The difference equal this one will be constructive, and the 2t equal this one is destructive. It is obvious, am I right? But if the distance is 2t plus half lambda, which means the distance is 2t plus half lambda, which means if it is constructive, here the distance will become 2t plus half lambda, am I right? Equal lambda. And yeah, you can see here it is just plus lambda. Does it make sense to you? Yeah. Any question? Does it make sense to you? Yeah, because here the lambda, yeah, the lambda should now the original lambda, it should be you should divide n here. Does it make sense to you? Because in the state film, and the lambda will change, and you can see here you just got this one. It's just the same thing here, am I right? And if 2t lambda divided equal lambda, yeah, which means 2t equal what? It's just like lambda. Does it make sense to you? Does this make sense to you? Yeah, because you can see here lambda plus 2, and here is lambda plus similar part here, am I right? So this one will be removed, and then 2t will equal this one. So which means for the yeah, which means for the only one wave undergoes a phase change, the effective path length difference is this one, and use the equation 70/40 for the destructive interference, and 70/50 for constructive interference. Does it make sense to you? Okay, Any question, just let me know. Okay, let's talk about one example, like example 77. Design an anti-reflection coating, like to keep unwanted light from reflecting from the surface of eyeglasses or other lenses. A thin film of a material with an index of refraction n equal 1.38 is coated onto the plastic lenses n equal this one, which means this is the thin film. This is like a after thin film. This is the material. And what is the thinnest film that will minimize reflection for lambda? Equal this one. The middle of the vision, like a light spectrum. Let's try to see the strategy. The film coats the plastic lens, so there is a reflection from the top of the film where it meets the air, and the bottom of the film where it meets the plastic. Yeah, we talk about that. We want to find the thickness for which there is a destructive interference between these two reflections, minimizing the overall refraction. So, which means, okay, let's prepare this. We follow the steps of tactics box 70.1. As the light traverses the film, it first reflects at the front surface of the coating. Here, the index of reflection increases from like air to like 1.38. So there will be a reflective phase change. The light then reflects from the rear surface of the coating. The index again increases from that of the film to that of the plastic. Yeah, that increase. With two phase changes, like the tactics box, like a 70.1 tells us that we should use equation like a 70.15 for constructive interference, because you can see here there are two phase change. Does it make sense to you? If there is no phase change or two phase change, and then you will use this one. And if there is only one phase change, then you need to use opposite. Does it make sense to you? Okay, let's continue. Like we can solve equation 70.50 for the thickness T that causes destructive interference like this one. Yeah, let's let me write it down here. This is 2T equal M plus N M equal 0, 1, blah, 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 blah. So which means T equal what? T equal lambda 2NM plus, am I right? So the thinnest film is the one for which M equal 0. That, yeah, that makes sense. It's obvious, am I right? So which means, yeah, we know the lambda, we know the N, then M equals 0. So we can calculate the T is 100 nanometer. Like interference effects occur when path length difference are on the order of the wavelengths. So our answer of like 100 and like 100 nanometers seems reasonable. Yeah, because the interference effects occur when path length difference are on the order of wavelengths. Yeah, here the wavelength equal what? This one. Yeah, it is on the order of wavelengths. Does it make sense to you? It is. Yeah. Okay. Let's continue. Like let's continue to talk about the interference of reflected light waves. Yeah, a thin film can reduce reflection, but it can also enhance reflection. It is possible to make something like a mirror with very strong reflections at certain wavelengths with transparent materials. This is important in biological systems. You have seen light reflected from the eyes of a cat or dog at night. I think this is familiar, very like a common phenomenon for us. Yeah, when you see the eyes of cat or dog at night, you will see there is a light reflected. It is a reflection of light from a layer at the back of the eye called the temptum lucidum. Like this is a Latin words for bright carpet, which reflects light back through the cells of the retina. give the cells a second chance to detect light, important to animals that must see at night. Yeah, well, that's the reason why our human eyes is not like that, because we cannot see at light. But for the animals, they have this needs, requirements, yeah, for surviving. So they have this their eyes have this structure, yeah, give a second chance to detect light. Yeah, does it make sense to you? This is the application. Okay, let's talk about the other example, 17.8. What light is reflected? This is a biology example. Like we know, like the sharks and the related fish have a very well developed temperature. The figure to the right here, figured here, shows a camera flash reflected from a shark's eye back towards the camera. This reflected light is much brighter than the diffuse refraction from the body of the shark. You can see this one is very bright, but this here, there are some reflection, but not that strong. The figure at the bottom right shows this figure shows the structure responsible for the enhanced reflection. It consists of two layers. Here is the first one, 2 layers. This is the first one. This is the second one. Yeah, and it consists of 2 layers of nearly transparent cells, which index of reflection is essentially that of water. Yeah, yeah, and which means here is 1.33 like that. Okay. And with a stack of gonad crystals sandwiched between them, there is a crystal thing. And light is reflected from an interface at both sides of the stack of crystals. And the reflection is essentially strong if there is constructive interference between these two reflections. If the layer of crystal is 80 nanometer thick, for what visible light wavelength is there constructive? Yeah, this is the question. If the layer of crystal is this one, which means the T is this thing. And what visible light wavelength is there? Constructive interference. Yeah, what we need to do that just write that equation to. Yeah, first let's try to get the strategy. We're looking for constructive interference between two fluxes. So we will use the steps of tactics box 70.1. The film in this case is a layer of crystals. We are looking for a visible light wavelength. So we will look for a wavelength between this one. Yeah, we have already talked about this. Like this is a visible light spectrum, like a wavelength between those two. And let's do the preparation for this example. Like for the front reflection in the figure above, in this figure above, like the index increases as a boundary, yeah, because you can see here the index is 1.33, here is 1.83. So it is the index increases at the boundary here. So there is a reflective phase change. For the rarer reflection here, reflection, the index decreases, so there is no reflection phase change. Yeah, like we talked about this before, like I think here you can see a light wave undergoes a phase change if it reflects from a boundary at which the index of reflection increases. Yeah, which means only the index of refraction increases, and then we can the light wave undergoes a phase change. Otherwise, it will not. So, sorry. Yeah, so which means there is only one. There is only further. Yeah, so there is only one reflective phase change. So we are thus looking for constructive interference with one reflection phase change. So we can use equation 70.15. Okay, so let's talk about how to resolve this problem. Yeah, we arrange equation 70.15 like here, 2t equal lambda n. This is the equation 70.15, and then we can get the lambda equal what? 2tn divide m plus 1 divide 2. Am I right? This one. So yeah, we know the t and we know the n, and we know the m here. We don't know the m, but the first possible solution is for m equals 0. So which means that like we just let yeah m equal, I think here it should equal 0. Yeah, let m equal 0, which means here is 2 there it should be removed, and then we get this equation, we get this result 590 nanometer for m equal 1, and here and we can get the here values. Yeah, if the m equal 1, yeah, we can get the higher values. We can and for m equal 1 and higher values, we get the wavelength beyond the visible light spectrum. So this is our our final result. You can see if you get let m equal 1, 2, and the result will greater than 700. It is beyond the visual light spectrum. So this is our final result. The reflection will be enhanced for wavelengths around 590 nanometer, which corresponds to yellow light. You can see. If you recall the visible light spectrum, this is just corresponds to yellow light. Yeah, in the photo, you can see here, the reflection looks distinctly yellow, a little yellow. Yeah. Okay, our calculation matches the real world, which gives us confidence in our result. Does it make sense to you? Okay, this is a biology example. Let's continue. Okay, let's talk about the thin films of air. Thin films of air. A film does not need to be a solid material. Like you can see here, we talk about it is just here is crystal cell. It is some a material. But here a film does not need to be a solid material. It can also be air. Yeah, it can also be air. Like a thin layer of air between two microscope slides pressed together can create light and dark fringes. You can see here. I think if you just put two thin plastic plate together, and between those two, and there are some air, and yeah, you can see there are some color there it can create light and dark fringes. The very air layer's thickness can cause constructive and destructive interference at different points between the slides. You can see here, this is obviously destructive, and this is the dark. The bright one is constructive. The dark one is destructive. Does it make sense to you? Yeah, the fringes can also be colored, which results from some wavelengths experiencing constructive interference, where others experience destructive interference. I think those two is just talk about the similar thing. Yeah, the fringes can also be colored. Yeah, here there are some color which result from some wavelengths experiments in constructive interference, where others destruct interference. Here is interference. Here is constructive. It doesn't make sense to you. Yeah, which means the a film does not need to be the solid material. It can be air. Yeah. Okay. Let's talk about the structural color from thin film. Structural color from thin films. For a 470 nanometer thick soup bubble, you can see. I think you guys always see this bubble, especially in some party thing. Light near the inside of the spectrum undergoes destructive interference, while light at the middle of spectrum undergoes constructive interference and is strongly reflected. Yeah, and the subfilm of this thickness will therefore appear green. Yeah, since the middle, like the green, undergoes constructive interference, which means the green will be empowered, and the end of the spectrum undergoes destructive, which means like the purple, the red will be destructive. Like so, the soup films, yeah, you can see of this thickness will therefore appear green usually. Yeah, you can observe it by yourself. Okay, in the but yeah, some of the most bright color. Some of the most bright colored animals and plants have little or no pigment. You can see actually here the bubble, if you it does not have colors. Yeah, only like when you see it in the light, it just reflects the light. Yeah, and then you can what you see is just the sunlight from in the bubble. Yeah, actually the bubble they are not colorful. Yeah, that makes sense to you. So like some of the most bright colored animals and plants have little or no pigment. Yeah, for example, this like a hamster. Yeah, there is no color here. Yeah, just like this is an example of structural color, like a color that depends on an object structure, not on pigment. Yeah, here are some structure, and this structure can can have some thin film interference, and then constructive some like variable like light, and destructive some variable the other variable lights. So then you will see it is colorful. But this one it does not have like a pigment or just a little pigment. Yeah, it's just the object structure generate this color, not like pigment. That makes sense to you. Like you can see here, this is the mother of pure layer inside an abnormal shell. It's made of transparent materials, but has stack of 500 nanometer planes that strongly reflect certain colors. Yeah, you can see here, it will strongly reflect certain colors. So when you wear like a pearl necklace, sometimes in the light, in the sunshine, it will give you some like a beautiful color. Does it make sense to you? Okay, let's continue. The change in color with the change in angle. Changing color with a changing angle is a hallmark of a struck color. Actually, when you want to see different color, you just change the angle you observe. Like when you this is your eyes, you see like this, or you see like this, there will be different color. That makes sense. Yeah, because here, which means the wavelength will be different. Yeah, and then you will see different color. Yeah, such colors are often called intradensate. Yeah, we call this intradensate. Blue pigments are very rare in nature. Yeah, you can see in nature, in the real world. Yeah, the blue pigments you seldomly see that some things are like a blue color. Am I right? Some get the colors from interference or diffractions, but others get their blue from scattering. Yeah, you can see, you may see some blue colors, but but this blue color from interference or destructive, or some from like a scattering. The random redirection of incoming light, yeah, just come from those waves, but it's not like a blue original like that. Okay. Air molecules in the atmosphere scatter light. Yeah, you can see the air molecules in the atmosphere scatter light, allowing long wavelengths to pass through and short wavelengths to scatter, which makes the sky blue. Yeah, because you can see we only can see the short wavelengths, like light wave. Yeah, the short wavelength light wave is just it will similar. It is just the blue one. Yeah, does it make sense to you? Yeah. So which means yeah, the sky there is no color for the sky. It's just like the the light, this air molecules scatter light, then we see the sky is blue. Does that make sense to you? Okay, let's check this quick questions. A film of oil index of reflection like is 1.2 and floating on top of an unknown fluid X with unknown index of reflection Nx. The thickness of the oil film is known to be very small, on the order of 10 nanometer. A beam of white light illuminates the oil from the top, and you observe that there is very little reflected light, much less reflection than at an interface between air and X. What can you say about the index of refraction of X? Actually, this question is a little bit tricky. You can see here, this is, for example, this is oil, and this is air. This is oil, and this is let me change. This is fluid X, and from air we know air air like a 1.0003, almost 1. Am I right? So like which means the index of refraction increase, right? So which means there is a phase change. Like it will be 180 degree, and then the question asked like, what can you say about the index of reflection? Firstly, let's talk about there is very little reflected light, which means the destructive like inference destructive inference come out, happens. Now constructive doesn't make sense to you because very little reflect light. But this one is very tricky because you can see the oil field is known to be very small, which means we can ignore the film distance. Yeah. So here we just need to think about the phase change from the oil to the from air to the oil, because the index of refraction increase, so there will be a phase change. Then if we want to it has a destructive interference, then we need to make the phase opposite. That makes sense to you? So which means we need to make the phase change again. So which means what? Which means this Nx should greater than N oil, because the if the index of refraction increase, and then there will have the phase change 180 degree. So which means for example, here I just this is air, this oil, and this is like a fluid X, and then it will like 100 and 100 change, which means it will have the destructive interference. Does it make sense to you? So this one is now you can now use the because there is no a film distance. Yeah, you can ignore that because it's so small. So what you just need to think about is the phase change, and you need to let it change opposite. Yeah, so which means this one is right answer. Does it make sense to you? Okay, let's continue. Yeah, this one is the right answer. Okay, and okay, let's talk about one conceptual example. Like what color is the film here? This film. Like the photo shows a soap film in a metal ring. Yeah, metal ring that is held vertically. Explain why the colors shift as you move down. move down the film, and while the film at the top here reflects no light at all. Okay, let's talk about it. The main reason is because of the pull of gravity. You here is gravity. The film is thicker here, is thicker near the bottom and thinner at the top. That makes sense to you. Now consider a greenish band on the film. At the thickness, the wavelength is of green light experience constructive interference, while those of red and blue light experience destructive interference. If we move to a lower position on the film, the thickness increases. Yeah, because you can see the gravity thing. The thickness increases, and so the path length difference increases, and the longer wavelength of yellow or red light experience constructive interference. The color changes. Does it make sense to you? Because of gravity, the thickness is different. In here, here is different here. Yeah, and you can see here the thickness is increases. And then the longer wavelength of yellow and the longer wavelength will show here. That makes sense to you? Yeah, show the and show the bottom. Yeah, that makes sense to you. Yeah, and the very top of the film is exactly extremely thin. It's very thin and thinner than the wavelength of light. When the film is very thin, there is almost no path length difference between the waves reflected off the front and the back of the film. However, the wave reflected off the back undergoes a reflective phase change and is on a phase with a wave reflected off the front. The two waves thus always interfere destructively, no matter what their wavelength. Thus, all reflection is suppressed and the film appears dark. That makes sense to you because here, yeah, the film is extremely thin, thinner than the wavelength of light. When the film is very thin, there is we can ignore the path length difference, just like what we talk about in the quick check, the question, the next quick check question. Between the waves reflect off the front and the back of the film. Like, however, the wave reflected off the back undergoes a reflective phase change and is out of phase with the wave reflected off the front. The two waves thus always interfere destructively. Yeah, no matter what their wave. Thus, all reflection is suppressed, and the film appears dark. Yeah, it's similar like the NASA questions. Yeah, because yeah, you just there are it's very thin. You just ignore that, and then you from the air to the water, and then from the water to some yeah you will have the like a destructive interference. Yeah, the absence of the reflected light at the top of the film may seem present, but our explanation makes sense given what we know about the thin films and reflection. Yeah, which gives us like a confidence in our reasoning. Yeah, you can see here. When we talk about the like a thin film, like there are some thin film interference. There are also some like uh, reflection interference. You need to think about both. Does it make sense to you? Okay, let's continue to talk about other things. Next, we talk about the single slit diffraction. Yeah, we talk about double slit diffraction and the diffraction grating. Yeah, and diffraction grating is just like the multiple like slit diffraction. Yeah, here we talk about single slit diffraction. The single slit diffraction is the diffraction through a tall, narrow slit of width A. Yeah, here there is a tall, narrow slit and the width A. The width is A. Yeah.
And the light pattern on the view screen consists of a central, here is a central maximum, and a series of weaker secondary maxima and dark fringes. The central maximum is much broader and brighter than the second maximum. Yeah, so this kind of phenomenon we call it a single slit diffraction. Okay, um, to understand this kind of diffraction, like we need to think about we need to think about the propagation of an extended wavefront. Yeah, and the Dutch scientist Christina like Huygens this develop a geometrical model to visualize how any wave, such as a wave passing through a narrow slit, involves. Yeah, let's talk about this Huygens principle. Like the Huygens principle has two parts. Yeah, like after we talk about this principle, principle, we will we can we will know much more about the propagation of an extended wavefront. Yeah, for the Huygens principle, there are two different parts. Each point on a wavefront is a source of a spherical wavelet that spreads out at the wave speed that spreads out at the wave speed. At a later time, the shape of the wavefront is a curve that is tangent to all the wavelengths. Yeah, this is the Huygens principle. Let's talk about more. You can see here the curve tangent. Here are some the curve tangent. So the curve tangent to the wavelet of a plane wave is a plane that has propagated to the right. You can see here it is initial wavefront. Here is the initial wavefront. And each point on the initial wavefront is a source of a spherical wavelet. Yeah, here is a spherical. The wavefront at a later time, here is a later time, is tangent to all the wavelets. Yeah, you can see here is a tangent to all the wavelets. Yeah, this is like a for this curve for the Huygens principle. Yeah, and like the curve like a tangent to the wavelets of a spherical wave is a larger sphere. You can see here if here is a wavelength initial wavelets front. And the wave front at a later time is tangent to all the wavelengths. Yeah, this is the Huygens principle. Yeah, it talk about two different situations. Yeah, and one is just the initial wave front is just in a plane wave, and each the this is the initial wave front, and the later time, the wavefront at a later time is tangent to all the wavelengths. Yeah, here. And for the curve tangent, yeah, for the spherical wave, this is the plane wave. The next one is plane wave. Here is a spherical wave. For the spherical wave, and this is a initial front, and the later time wave front is tangent to all the wavelengths. Yeah, this is Huygens principle. Yeah, let's based on the Huygens principle, let's analyze the single slit diffraction. Yeah, according to Huygens principle, yeah, each point on the wave front can be thought of as the source of a spherical wavelength. Yeah, you can see here. If this is yeah, here is that like a slit, single slit, and this is the initial wavefront. And according to the Huygens principle, each point here on the wavefront can be thought as a source of a spherical wavelength. Yeah, here. Does it make sense? These wavelengths overlap and interfere, producing the diffraction pattern seen on the view screen. For example, uh, here is like a view screen, and the wavelengths from each point on the initial overlap and interfering, creating a diffraction pattern on the screen. For example, here is the screen, here is the screen. Yeah, does it make sense to you? Yeah, based on the Huygens principle. Like the path of several wavelengths, as they travel straight ahead to a certain to a central point on the screen are nearly parallel, and so they are in phase. You can see here. The wavelengths going straight forward all travel the same distance to the screen. Thus, they arrive in phase and interfere constructive to produce the central maximum. Yeah, because that's the reason why the central there is a big central maximum. Yeah, because the path of several wavelets as they travel straight ahead to a center point on a screen are nearly parallel, and so they are in phase. The screen is very far to the right in this view of the slit. Constructive interference will occur, creating the central maximum of the distraction pattern at theta equals 0. Yeah, when theta equals 0, it is parallel. And then to the central, yeah, this is a screen view, and they just to the center, and they will have a bright and a broad like fridge. Doesn't make sense to you? Okay. At a point away from the center of the screen, yeah, for example, this is the center of the screen, away, this is the center, this is away from the central screen. Interference occurs, you can see the wavelengths 1 and 2, for example, wavelengths 1 and 2, yeah, starts a distance to a divided 2 apart. If lambda r12 is if delta r12 is half lambda, you can see here. This is r12. This is r1. This is r2, and you can see here is the distance between r1 and r2 is half lambda. Then the wavelengths are alternate phase and interfere destructive. Does it make sense to you? Because we talk about that. If the distance is half, like a half wavelengths or like a multiple wavelengths plus half wavelengths, it is like alternate phase and the interfere destructively. If delta r is the distance of r1 and r2 is half lambda, then so are r3 and 4. Yeah, r3 and 4 is the same thing, similar thing. Does it make sense to you? Yeah. And r like the distance between r5 and r6, so perfectly destructive interference occurs. So like if it is now in the center, it will have the destructive interference occurs. Yeah, that makes sense to you. Okay. Like every point on the wavefront here can be paired with another point that is a distance half a away. Yeah, because here is a half a and b is half a and 2. 1 and 2 is half a, and 3 and 4 is halfway. 5 and 6 is halfway. Yeah, half a away. The condition for destructive interference is the distance between like r1 r2. Yeah, is a here is and here is theta, which means this one. Let me put it clearly. Yeah, here is theta. Here is theta. And then like this is two half a, and then this distance between r1 and r2 is 2 half a multiple sin theta 1 theta, yeah, theta 1 or theta is a similar thing, and equal half, because we know this is viscosity is half lambda. That makes sense to you? And this, we have this equation. The condition for the destructive interference is this. Yeah. If this situation, if like the distance equal this one, and then the destructive interference happens. Okay. Like the general condition for complete destructive interference is A sin like theta p equal p lambda, p equal 1, 2, 3. Yeah, which means the condition for the dark fringes in single slit destruction with slit width A. Yeah, you can see here like P equals 0 is specifically included because P equals 0 is the central maximum. The equation for all other P's locates the minima. Yeah, that makes sense to you. That P equals 0 is the central maximum, and other is like a locates the minimum. Okay. Yeah, you can see. Yeah, because here this one equals this one to A sin theta equal to lambda, which means 2, we remove 2. A sin theta 1 equal lambda. Am I right? So like this one, we just use P theta 1 with theta P, replace theta 1 with theta P. Does it make sense to you? And this is why this equation we get. Then here, yeah, here is just like a this is when the P is 1, when the P is 2, like it will be A sin theta 2 equal to lambda. Here is 1. Does it make sense to you? Okay. And yeah, and where theta P like much smaller than 1 radians. Like most situation, we can use the small angle explanation to give, because which means in a very small theta p, will sin theta p equals sin theta p. We have already talked about a lot, and which means that theta a theta p equal p lambda, like theta p equal p lambda divided a, and we have this equation. That makes sense to you when the theta p is much smaller than 1 radians. Okay. That's it. The bright central maximum. Here is a bright central maximum at theta equals 0, which means here everyone is just parallel. Yeah. And has the highest intensity in between the dark fringes. Here is here. In between dark fringes, the intensity varies smoothly. Yeah, you can see this is the biggest, and then smaller. Yeah, that makes sense to you. Okay. And let's talk about the west number, the single slit diffraction pattern. Here, YP is the distance. YP is the distance from the center of the central maximum to the P dark fringe. Here, this is the central maximum to the P dark fringe. Here is the dark fringe. Here is the other dark fringe. And this distance, we call it YP. That makes sense to you. And YP equal what? Equal L tangent theta P. Because here, this one is L. Am I right? Which means this one is L. And this is the theta. 1, 2, theta P. And this one is like L multiple tangent P. It obvious, right? The dark fringes in the single slit diffraction pattern are located at this one. Yeah. Yeah, because we know like the theta P equal this one. Am I right? And here. Sorry. And here we also can use like a small angle approximation, approximate that's small single. Here there we also can use small angle approximation. Yeah, and then the tangent theta equals theta. Tangent theta p, tangent theta p equals theta p, which means it equal L theta p. And the theta p was that we have already talked about here. So which means like YP equal this one. Yeah, because theta p equal p lambda divided a, and this YP and p equal 1, 2, 3. That makes sense. This is the positions of dark fringes for single slit diffraction with screen distance L. Okay, this is how to calculate the position of dark fringes. Okay, and the width of the single slit, the width W here, two different the width W is two different dark fringe, and but they are the same. They have the same like distance with the central maximum, and the width W of the central maximum is defined as the distance between the two p equal 1 minima. Yeah, here is 1. Here is 1, and this is the distance. The y we call it y W, and which is simply equal what? To 2 multiple y1, right? For the p equal 1. So we know like the y1 equal what? Here. Here we know the y1 equal lambda L divided A, am I right? So which means like to the W equal so it is equal like a lambda L divided A, so W equal 2 lambda L divided A. What this is the width of the central maximum for single slit diffraction. Does it make sense to you? Like a counterintuitively, the smaller the opening a wave squeezes through, the more it spreads out on the other side. Yeah, which means if the smaller the opening, which means A is decreasing, right? Which means the W will be increase. That makes sense to you? Yeah. So the more is spread out on the other side. Okay, let's talk about some interesting thing for the single slit diffraction pattern. Yeah, you can see if a laser beam shines on a thin wire that blocks the beam itself, the pattern shows up in the image to the right, this one. And the image appears the same as a single slit diffraction pattern. And you can see it's just the same as a single. This is the maximum, and this is some minima, and then it will smaller. Yeah. So which means in some situation, a single slit diffraction pattern will happen in other situation. The other one is Babinet's principle states that the diffraction pattern from an optical body is the same as that from a whole oscillator of the same size. Yeah, interesting thing, am I right? So, yeah, this is what you just need to know. And let's talk about some quick check questions. Like a laboratory experiment produces a single slit diffraction pattern on screen. Here, if the slit is made narrow, the bright fringes will be what? Which means if the slit is made narrow, which means the A is increase. Am I right? Sorry, the A will be decrease. And then the bright fringes, we know that the here is the we just the this is the distance. Distance will be like a increase. Am I right? We have all talked about it, and which means it will be further apart. Yeah, it will be like become will increase. That makes sense to you? Yeah, further apart because you can see the minimum between the batch fridges at this one, which means this one if it is increase decrease and it is this one will be increased. Actually, the dark I just show you the dark fridge. And the bright fridge and dark fridge is a similar thing because the if the dark fridge like it become bigger and the bright fridge will also like further apart will become if the dark fridge will further apart and the bright fridge also will be further apart. Does it make sense to you? Let's check this question. Each of the slits is separately illuminated by a broad laser beam, which produces a broader, brightly illuminated region on the screen at the right. Yeah, we have already talked about this. Yeah, like since here, yeah, it's a similar thing. Since like if you want like the bright fridge is wider, like which means you need to decrease the the slit distance. So which means which one? Yeah, A is a smaller one. The smaller one will like produces a broader, brightly illuminated region on the screen on the right. That makes sense to you? Okay, so this is A. And let's talk about the other one. A laboratory experiment produces a double slit interference pattern on the screen. If the left slit is blocked, the screen will look like, yeah, this is a double like a slit interference. If the left is blocked, which means it will become single slit interference. Yeah, which one is a single one? Yeah, which means this the single one means like the maximum, the middle, the central maximum will like a broad and other like a decrease like as to the other one. So which means this one is the right thing. Does it make sense to you? Okay. Yeah, the D is the right answer. And let's check this one. A laboratory experiment produces a single slit diffraction pattern on a screen. The slit width is A, and the light wavelength is lambda. In this case, which means this is a typical single slit diffraction. Yeah, we know that like here, here. Yeah, because we know like the theta is very small. Yeah, like most situation is very small, which means the lambda divide A will be very small. Am I right? Does it make sense to you? Which means the lambda should much smaller than A. Doesn't make sense to you because you need to P is just a 0, 1, 2, 3, yeah. And if you want this value is very small, which means this value will be very small, which means this one will be much smaller than this one. Does it make sense to you? Yeah. Which means the lambda will be much smaller than A. Yeah, so we need to choose A. Does it make sense to you? Okay. Let's talk about one example, using diffraction to measure the width of a hair. A student is doing a lab experiment in which he uses diffraction to measure the width of a shaft of her hair, and she sheds a 530 nanometer green laser pointer on a single hair, which produces a diffraction pattern on a screen like 1.2 meter away. The width of the central maximum of the pattern is 40 millimeter. Like what is the thickness of the hair? Thickness of the hair. if he choose a wider shaft of hair, how would this change with width of the central maximum? Okay, let's talk about the strategy. The diffraction pattern produced by a hair of width A will be the same as that from a slit of width A. So we will like we are given the width of the central maximum. So we can use equation 70.20 to analyze the situation with A as a width of the hair extent of the width of a silt. What is silt A? Yeah, what slit A? Sorry, slit A. What is the thickness of the hair? Okay, actually the equation 7020 is W width equal what R 2 lambda L divided A, which means the A should equal 2 lambda L divided like a width. And we know that the width is 40 millimeter, 40 millimeter. And the lambda, we know that, and the L, we know that. So we can easily to calculate the width of the hair. That makes sense to you? Yeah, for a single slit, we know that a wider slit gives a narrower pattern. So the same is true for the hair, which means if like choose a wider hair, which means it will be become like a narrow pattern, will give a narrow pattern. This is a fairly technical value. Yeah, this one. This is which means this is like a hair width. This is a fairly typical value for the thickness of hair. So our result is reasonable because you can see the hair, the thickness of hair is very small. Okay, let's continue. Let's continue talk about the circular aperture diffraction. Yeah, diffraction occurs if a wave passes through an opening of any shape. But an important example is a circular aperture, like light waves passing through a circular aperture spread out to generate a circular diffraction pattern. You can see here, it's just like this. Most of the intensity is contained in the circular central maximum, which is surrounded by a series of secondary bright fringes. You can see it's very similar to the like a single silt direct diffraction. Yeah, the difference is just like the single silt diffraction is just like it's just like this, and the circular is just like it's the pattern is circular. Yeah. And so like the light waves passing through a circular aperture spread out to generate a circular diffraction pattern. Most of the intensity is contained in the circular central maximum here, which is surrounded by a series of secondary bright fringes. Yeah, we have already talked about this, and let's continue. Okay, let's talk about the if the angle theta1 here. Theta1 here locates the first minimum in the intensity for a circular aperture of diameter d, and this theta1 equal this equation. Yeah, we can calculate the theta1 using this equation. Actually, there is a 1.22. This is from a theory called like a airy pattern, and this airy pattern there is like a constant, like there is a first zero of Bessel function occurs at approximately 3.8332, and then it should be divided pi equal this one. So this is just a constant for this situation. You just need to remember this 1.22, and for the yeah, actually initially it is sin theta 1 equal 1.22 lambda divided d. But because this theta 1 is very small, so we can write theta 1 equal 1.22 lambda divided d. And yeah, then we can get the western of the central maximum on the screen. A distant L from the aperture is this one. Yeah, because we have the like 1720 equations like a W equal to lambda L. Actually it's a similar thing. It's just like a it's just equal like a to let me tell you. Wait me for a moment. Yeah, because yeah, like the lambda equal like the only the y is equal this one, and here the a is d for here, and the 2 lambda l is just this one. So it's just like multiple 2 and this equation. Yeah, we can use this equation for west of the central maximum on screen. Yeah, does it make sense to you? Okay. Like the diameter of the diffraction pattern increases with L. With L, the wave spreads out as it travels, but decrease with the increase in D. You can see here if we according to this equation, and we know like as a diameter of the diffraction pattern increase with D with L, and but decrease with like a increase in D. Okay, and the same principle for sorry, I think you need to I need to add more details for this one. Here this one W equal what? W equal 2.44 lambda d, am I right? Lambda LD. Yeah, so which means this one, if the L increase and then this Y increase, if the D decrease, if the D increase, this it will decrease. Yeah, this is just talk about this equation. And the same principle for obstructions applies here as well. The diffraction pattern from a circular obstruction is the same as for a circular aperture. Diffraction once again shows the wave nature of light. Okay. Yeah, this is we learn about the circular aperture diffraction. Yeah. Okay, let's continue to talk about some examples. Finding the right viewing distance. Light from a helium neon laser, the wavelength is equal 633 nanometer, passes through a 0.5 millimeter diagram at hole. How far away should a view screen be placed to observe a diffraction pattern whose central maximum is 3 millimeter in diameter? Yeah, the size of the central maximum is determined by the wavelength and the aperture size, which are given, and the distance to the screen, which we will determine. Yeah, we can rearrange the equation 17.23 to solve for L, the distance to the screen. Yeah, we can use this equation. Actually, W will equal what? W equal 244 lambda LD. Then like L equal WD divided 2 lambda. I'm right using this one. Yeah, we know the width. Yeah, it is just this 3 millimeter. Yeah, like this is a diameter, and also we know the slit width, like it is 0.5 millimeter. So Yeah, and then we know the lambda. Yeah, so we can calculate the screen distance is 0.97 meter. The hole is relatively large compared to the wavelength of light, so the spreading will be relatively small. To see a central maximum of the notice size, we expect a large screen distance. Yeah, so you can see this screen distance is quite large. It's almost 1 meter. 等于3区. Okay. Okay, you can try this yourself, observing the diffraction. To observe diffraction from a circular aperture, use a pin to prick a very small hole in each of two pieces of aluminum foil. Tape one piece up to a window that faces the sun, then holding the other hole close to your eye, observe the sun through the pinhole on the window. You will see clear diffraction fringes around the pinhole. How do the fringes vary if you change the size of pinhole near your eye? Yeah, you can try it. But don't look directly at the sun, except through the two pinholes. Yeah, it will be a little dangerous. Okay. Yeah, this is what we talk about today. And yeah, let's do a summarize for like chapter 17. And firstly, we talk about some general principles. Yeah, we know like the light. Yeah, they have a different model to represent to have different character features because this like chapter we mainly focus on the wave model. The wave model considers light to be a wave propagating through space. Interference and diffraction are important. The wave model is appropriate when light interacts with objects whose size is comparable to the wavelength of light. You can see there is the object size. Yeah, usually it will be comparable to the wavelength of light, or roughly less than about 1 point millimeter. This is what we talk about in this chapter. And also we talk about Huygens principle. See that each point on a wavefront is a source of spherical wavelength. Yeah, you can see. A wavefront is the source of a spherical wavelength. The wavefront at a later time here is tangent to all the wavelengths. Okay. And also we talk about some like important constants. The index of refraction of a material determines the space of light in that material. Yeah, this is the like the light in this material, which means this is the light speed in vacuum, and this is the index of refraction. The index of refraction of a material is always greater than 1, so that the velocity is always less than like the velocity in vacuum. The wavelength lambda in a material with index of refraction n is shorter than the wavelength lambda, the wavelength in vacuum. Yeah, like this in vacuum, it equal lambda. The wavelength lambda equal this one. The frequency of light does not change as it moves from one material to another. Yeah, the wavelength change, but the frequency will not change, which means the period also will not change. Okay, there are also the other like important constants. The diffraction is the spreading of a wave after it passes through an opening. Here is an opening, and if there and it will have the diffraction phenomenon. Constructive and destructive interference are due to the overlap of two or more waves as they spread behind the opening. Yeah, there are some like constructive or also destructive. Yeah. Okay. Also, we talk about some applications. Like the first one is diffraction from a single slit. Yes, a single slit of wax has A has a bright center like a maximum of wax. This is the wax. We can use this equation to calculate. This is flanked by weaker second maxima. Yeah, you can see the second maxima and it's very weak. And okay, and also the dark fringes are located at the angles such as this. You can use this equation to calculate the dark fringes angles. Yeah, if the lambda divide is much smaller than 1, then from the small angle approximation, yeah, we can get we can get the angle using this equation, and also we can get the distance between two like two different like frames. Yeah, this one, this sorry. Yeah, this one, this one, this one, this one, and we can get it using this equation. Okay. Also, we learn some like interference from multiple slits. Waves overlap as they spread out behind the wavelengths overlap as they spread out behind the slits. Okay, like yeah, we also talk about some interference from multiple slits. Waves overlap as they spread out behind the slits. Bright fringes are seen on the viewing screen at a position where the path length difference, delta r between successive slits is equal to m lambda, where m is an integer. Yeah, also, we talk about double slit with separation D. Equally spaced bright fringes are located at here is we can get the bright fringes using this equation. Yeah, we have talk about it, and yeah, okay, yeah. And then we talk about some interference from multiple slits, also from multiple. The fringe spacing is this one. Yeah, we just got it from these things. Yeah, and the diffraction grating with slit space D. Very bright and narrow, fringes are located at angles and position. We can using this equation. Yeah, we have talked about this, and also, we talk about the circular aperture of diameter D, like a bright central maximum diameter. We use this equation to calculate it. It's surrounded by circular second maxima, and the first dark fringe is located at this equation. Yeah. Also, this is the angle. This is the distance. And for an actor of any shape, a smaller opening causes a greater spreading of the wave behind the opening. Yeah. Yeah, we talk about this. Yeah, a smaller opens cause a greater spreading of the wave behind the opening. If the opening is bigger, it will cause a smaller spreading. That makes sense to you. Yeah, because of the because here the D is here. This one decrease and this one increase. This one increase. This one decrease. That makes sense to you. Okay. Yeah, and also we talk about some thin film interference. The interference occurs between the waves reflected from the two surface of a thin film with index of refraction, and a wave that reflects from a surface at which the index of refraction increases has a phase change. Yeah, this is the equation how for the thin film interference how it happens how and when it is constructive, if there is 0 or 2 phase changes, and then you can use this equation for constructive, use this equation for this constructive. But if there is only one phase change, you can use this one for constructive and use this one for destructive. Yeah, we have talked about this before. Yeah, this is all we learn in this chapter. Yeah, in this chapter, we mainly focus on the wave model for the light wave model, and because for the light wave model, you can see there are some different situation. If the light goes through a hole or multiple hole, there are some situation phenomenon to happen. Also, if it from one material to the other material, the light also have some changes, and how this change and how you can use all those equations to calculate it. Yeah, this is what we learned in this chapter. And in that next chapter, we will talk about the ring model for the light. Yeah, it's for the next week's content. Okay, yeah.
So this is today's class. Okay, bye.